and we're here to talk about the Debian OpenSSL bug that you've probably all heard about. Little Dilbert cartoon for you. Basically, in May of 2006, there was a hopeful Debian developer trying to fix some bugs, and in fixing a bug, he actually introduced probably the worst bug that Debian has ever seen, and it's pretty amazing what widespread effect just a couple comments have created. And so we're going to go into detail about the actual bug and how the bug can be exploited in various different ways, different applications that are affected, and it'll be hopefully interesting to you.
Yeah, the Debian bug is probably, as Jake said, the most widely spread cryptographic vulnerability on the internet at the moment, and certainly has been much wider spread a few weeks ago still. And it really all boils down to cryptographic keys and the entropy. Cryptographic keys are used very widely to secure systems, to authenticate users, to sign data, and pretty much any other application where security is used. So cryptographic keys are very much at the foundation of internet security. And cryptographic keys are only good if they're hard to guess. Much like your password on your computer. If it's easy to guess, then it's no good if somebody can just try all likely passwords and find the one you're using. So the hardness of guessing a password or a cryptographic key is measured in entropy. That is, the number of bits at least needed to describe it. And so with a password, for example, the entropy grows as the password is longer, but it also grows as you use more different characters. Windows passwords have been broken for years, since they have only 36 bits of entropy, so any rainbow table, any type of that can break it. We'll see that the Debian vulnerability decreases that to 15 bits. So where 30 bits is weak, 15 bits is just not any security at all. And for any system to be secure, you need about 80 bits of entropy. Now, these cryptographic keys and all the different applications that are used are typically generated from one packet, the OpenSSL packet, that was started to provide secure communication on the internet, but now provides all these very useful tools that other programs use to generate their cryptographic keys. Tor, for example, to provide anonymity, administrative utilities such as SSH, but also all kinds of other applications where cryptographic keys are used. Now, to generate cryptographic keys on a computer, the OpenSSL packet has to acquire randomness, basically. So imagine you have to come up with something random in a deterministic program. That's kind of hard. Linux or any Unix system pretty much already does the work for you mostly by collecting random events such as user input, kind of, for example, the speed at which you type, the exact path through which you move your mouse. All those things are collected and provided in a urandom. Now, OpenSSL doesn't consider that sufficient and adds a few other things on top of it. It adds the process ID, which also changes every time you call the program, this key generation program, and a few other things. And one thing it also does is it uses to bootstrap its entropy memory that has never been written to, at least not from this process. So imagine you read some memory cell that you didn't write to. It's basically random, its content, at least not very predictable. Now, that led some Debian developer to think about why somebody would ever read from memory before writing to it.
And that's basically the irony of this vulnerability, is that of those sources of entropy, the uninitialized memory is actually the weakest, because it's not like you're actually getting the memory from the chip, it's the memory from the address. You know, basically it's initialized memory, so it's basically just leftover stuff from the stack. And so basically knowing the program, knowing the state, you'll know what those values are. So it was kind of a half-baked idea in the beginning. And then Debian developers, is looking to improve the software, and they're using a software called Valgrind. And what Valgrind does is it looks for memory leaks, and it looks for these cases where you're using uninitialized memory. And basically, if you're using uninitialized memory before it's initialized, this actually also can be a security vulnerability. And there's a lot of cool bugs this way. But in this case, he was trying to get rid of those vulnerabilities. And so he's like, oh, Valgrind complains. Let's comment this out. We don't really need to use this uninitialized memory because it's kind of worthless. And
VALGRIND?
that's correct.
Yeah, rid of
VALGRIND.
And actually,
It's a good tool.
To be fair, there's also the Debian developer that did this apparently did not see the FAQ about the Valgrind error on the OpenSSL website. That was pretty specific, like Valgrind has an error in this, just ignore it. But then there's also the fact that he did ask, the Debian developer did ask on the OpenSSL dev mailing list, which is not the OpenSSL team mailing list, which means that anyone could answer that, and it's not an authoritative answer, even though an OpenSSL developer did say if you're trying to have some, like you're trying to solve some problems with debugging, or if you want to figure out what's actually going on, it might be useful to, get rid of those errors. But I don't think that, and no one would say that the OpenSSL team blessed that patch and said that was a good idea. Although there's definitely some dispute about whether or not that's a reasonable thing that an OpenSSL developer could reply on a dev mailing list saying that. But it seems pretty clear that it wasn't like Ben Laurie signed off on the patch and integrated it upstream in OpenSSL.
Yeah, well, importantly, OpenSSL didn't integrate it upstream.
Right.
I mean, this was basically a patch that that stayed in the distribution. And one could say that basically the only patches you should make to software, in the distribution, especially with crypto, is like where you're going to install the files. You shouldn't change how it works. And what he did is the developer just got overzealous and uncommented out, or basically commented out the instance where the uninitialized memory was used, and then they went and commented out another instance of it, and that one was basically where the first source of entropy, dev_urandom, the real one, that's where that was seeded into the random number generator for OpenSSL. So just because you have
the bug was patched in the worst possible way by also removing a lot of other things that contributed randomness.
And one thing that's really beautiful about the patch is it's deceptive in how simple it is. It's a multi-line comment, so you see two insertions, /*, a comment, stop making this have an error, and then the line, which is not changed.
Oh, should we look at it?
And yeah, we should look at this. It's beautiful because upon first looking at it, you.
Screen is much smaller. Do we have it? Yeah.
There it is. So if you notice, the MD update and the MD update are both commented out, but it's kind of non-obvious that it's commented out because you see it's not green, it's not changed, but in fact it's not in effect anymore. So just looking at that patch, it looks like at just a quick glance that it's not really a big deal.
Right.
I mean, the first time someone recently saw this patch, they're like, oh, they just added a comment, it's not a big deal. But actually, like, whoops, that's the worst bug Debian's ever had.
Yeah. And what's funny about this is you can tell this page is very popular. If you Google OpenSSL, SVN, and trunk, you get a link to that diff. So that is the most popular search result.
And the problem is clearly not limited to a single version of Debian. It has been in the Debian stable for a year, but it has from there been taken into other distributions that build up on Debian, including very popular Ubuntu, which I think is the most popular desktop distribution. So it has spread very widely into many distros and has only after a year, in May of this year, been patched.
And the interesting thing about the patch is, in violation of Debian's own policy on the issue, at least from my reading of it, they publicly patched this before they disclosed the bug. And the interesting thing, if any of you are familiar with the deny hosts package, they have a nice little graph. And the graph showed an increase of brute force attempts basically after the patch but before disclosure.
Mm-hmm.
Like an incredible, like several orders of magnitude higher. And there are a couple of news articles written about this. Unfortunately, we couldn't get the graph because the deny hosts website doesn't keep like aggregate stats that you can get from a specific date. It would be kind of neat to have that if anyone has it, but couldn't find it.
So you're suggesting that people looked at the patch and worked out what the patch had fixed and were trying to attack?
Yes.
Yeah. It's for all security bugs, there's a lot of people watching every Linux kernel, change, regardless of what the comment says. They check to see if it has security ramifications. People are obviously reverse engineering Microsoft patches. There's no reason to believe that people aren't doing the same for distribution updates as well.
Yeah. People even look at binary updates a lot. All Windows patches are reverse engineered to see what vulnerabilities they patch. So having a source code update is so much easier to look at.
Yeah, that's all good.
Yeah.
Yeah.
Yeah, so different programs are affected by this. Pretty much any program that generates cryptographic keys using the OpenSSL library, one of which being SSH, that's used as a secure login to servers. So it's used by a limited number of people, pretty much everybody in this room probably, but not a large fraction of the internet population. But it does affect most systems, since the system that you get your data from, that you trust, might be affected by some admin having a weak key. And SSH uses a number of different keys, and all of them could be affected. So they're the host keys that on first login, you tell your SSH, yes, you trust this host, and every time you log in, your computer locally will check whether the fingerprint of that machine has changed to prevent man-in-the-middle attacks. So now, given that these keys can be broken, the servers that you trust can be spoofed. Other keys are used for passwordless login. So you tell the server to trust your key and to let you log in without giving any other credentials. And those too can be weak. So if, say, the root account has a weak certificate, these can easily be brute force. There's only 32,000 different ones on any given architecture, 15 bits entropy, and those can all be tried. Nice side effect is that that does not leave a trace in the log. So if you provide a wrong password, it will create a line in the log. If you provide a wrong certificate, it will not in most cases. Now the last keys, and the ones that haven't gotten much attention with regards to this bug, are the session keys. So to provide forward secrecy, we'll get to that in a minute. Initially, in each session, a new key is generated that both parties agree on, and then those user keys or host keys are used to sign that key, to make sure that both parties agree on that. Now, those session keys too can be vulnerable, and since the session keys are generated at the beginning of each session, they can be vulnerable if one of the computers is vulnerable, and not necessarily any key that you can look at. So all the tools that have come out to fix the SSH program, they search on your computer for weak keys. If you, though, without having a weak key, log into another computer who doesn't have weak keys either, but has a broken OpenSSL library still, those session keys are predictable.
Right. So basically, the issue is the Diffie-Hellman key exchange, and there's an interesting. I mean, this particular thing was something that I had thought was theoretically possible, and I was starting to work on a tool. And then in researching the tool, I found that someone else had actually already written the tool and released it. So these guys are badass, from what I can tell. Basically, they wrote. So the three tools that are up here are pretty much self-explanatory. But basically, it can generate the first key. We haven't tested this, but it seems reasonable from reading the OpenSSH source and also from understanding a little bit about the protocol and discussing it with people that are more knowledgeable about it than myself. You have a couple of things you can do. Even without the weak keys, the secrecy of the OpenSSH conversation relies on the Diffie-Hellman. And if either of the secrets chosen by either side is weak, then you are screwed. And this tool will take a PCAP file and decrypt those sessions, and it'll also extract the authentication keys from the conversations.
So basically, your password can be decoded through that if the server you logged into uses a weak OpenSSL.
Right, and so they also wrote a tool, BFSSH, which is just over the top. It's ridiculous. They didn't need to write this. SSH already allows you to toss in a number of identity keys. Most people have their server configured, like most Debian people have their server configured by default to allow 6 different tries. So that means you can try 6 different identities. SSH, just normal in a loop in like bash, you could call 6 keys at a time and try and log in, and if you have a success, you could narrow it down pretty easily. But they just wrote a tool that tries everything, and in 10 minutes, they can get an entire set of keys on for a given architecture.